maxillary patients, and now it's getting, you know, so bear with me, you know, if I need to move on, if it's too much. But this is the cases that we are seeing every day. This was also a patient, walked around, I think, 7 years with this big tumor growing. And then from there, it's sometimes, you know, accessibility. It's actually, I must be careful if I say, sometimes the system is failing them, you know, to be honest. And then, like, when we got involved with her, both eye sockets had to be removed. This whole tumor, she couldn't breathe anymore, things like that. And we ended up with the right side, your right side, is the 3D printed. I wanted to bring this model along, but it didn't fit into my suitcase, because you can just think of the size of that tumor. The 3D printed implant, then it was just after operations, and then this is the lady, yeah, that was a month after operation. Again, just the process flow. So we will go from the CT scan, pre-op model, design. On the pre-op model, and in the future we will have online planning software. And that's a standalone, that you don't need to buy all the implants from Stryker if you use their software. But where the doctor can indicate where he wants to cut, you know, he wants to have a resection, that line. So all of that will be done electronically. And then, yeah, the next slide is now in theater. So that's the size of the tumor with a cutting guide that was 3D printed. So again, I was talking about this reduced theater time. If we use this and you get it right, it's really not so easy. People are saying, yeah, just design a cutting guide, but you must think of where the tumor is growing to, which perimeter are you using. If we see a CT scan, then remember, it's stripped from all the nerves, all the arteries, all the soft tissue, it's just the bone. So how do you design that to actually fit? And we must be, as designers, engineers, we must be in theater to actually see this. So it's not the nicest, but this is working very good. So you can really save maybe 30 to 40% theater time by using this. And we're trying to convince now the discoveries and all of these big medical insurance companies that this is the way forward. We did you can go and have a look at the video that was covered by Carte Blanche, 3 mandibles, 1 day. And again, here was a reduction of around 35%. Follow-up, it's very important for us to do the clinical follow-up, and then also in our ISO environment to bring that information back. Just to show you some evolution. You know, where we started off, it was a very solid design, and Hein was also talking about this modulus of elasticity, that you can, you know, if you design it very solid, you can pull a car with it. But at the end, you don't need that. You maybe can work with a very fine lattice structure, where you can have osseointegration or blood supply in this case. The bottom left is actually bone fragments that was just grind and then put with blood supply. And you want then a solid bone in that area. But the need is extremely high. You know, I was at KZN last year, and just a morning session, there were 8 patients that needed. Some of them is tumors, some are trauma. I'm not gonna, because then I said we must embrace, and you know, we must, but the reality is some of those patients will wait 3 months for a CT scan before we can start working on that, and that's not right. What if you are, and that was the case, 2 were shooting, you know, it was trauma cases, and then they attached the bottom jaw to the top jaw up to a point where the CT scan can take place. So, and you are on a liquid diet. So what we're trying to do is also conventional versus additive. Additive is not always the best. The golden standard still is a fibula flap, where you take the patient's own bone, but you can't do that in the smaller centers. An operation like that will cost 800,000 rand with microsurgery, they are attaching the veins of the bone inside the neck. There are so many risks. You know, and the reality is just it's not possible for all the patients. I need to speed up and share with you the good stories. This is custom design pelvic implant. It was 3D printed by us. It was designed by Professor George Vikatos. So it's not just small things. It can be bigger implants. We did a whole hemi-pelvis, so half size of the pelvis. But you can end up with very nice designs where you really push the technology. You will see here the osseointegration, the two surfaces, where you want very fine pins where the bone attach. This is an ankle implant that was tested. It was implanted. Remember, just you can't. I will get quickly to the regulatory side and our ISO. And it's not just I decide today I want to try this and put it into a patient. You know, that's not happening. Even though that we are sticking with the TR64 material, even the designs, there must be product risk assessment, process risk assessment. So now you must be, you know, these are quite sensitive slides. What will happen is in the state hospitals sometimes they will remove the cancer, but then they will send the people back home. So they will remove the tumor and then no reconstruction. There's just not enough beds available, theatre time available. So there are many of these patients walking around. And the problem is, on the one side is you need skills to, you can think for yourself, to manufacture these clip-on faces. We are not there yet that we can print silicone that fine with the right color tone, all of that. We're not there yet. They are trying to get that right. But on the one side, nobody deserves to walk, you know, like this. I think it's good that this screen is, you know, going on and off, but it's really, this was the gentleman that I showed the first video of. We 3D printed left, right. That was his, that's the nose prosthesis, and then the right side is the clip-on face. So this is a bit tough to see, you know, but if they remove your top jaw, you can't swallow, you can't speak, you can't, you know, you can't eat, and this is where we try. It's not perfect, but at least it can go out. Let me just move on. At least it can go out. And we're doing also auricular prosthesis where we combine digital design with actual drill guide, cutting guide, you know, where we can manufacture the silicone prosthesis, and again many children. You will see, your top right side is a 6-year-old that we actually helped the other day. We started off also trying to fix it to the top jaw, but not everybody have teeth. You know, then it's on soft tissue it doesn't work very good. So there was also some design evolution, and where we started off just with a drill guide that we exactly know what angle, and we can indicate for the doctor the skull is there 5 millimeters thick. But we use it now also as a mold. So what's a good story is he asked that we actually scan his sister's ears because he liked the shape. So we had to fly down from Bloemfontein and come and scan the sister's ears and then shape the molds and all of that. And I think Jansie was present the other day where he presented at the Carl Emil Fuchs Foundation and the impact of actually what this done to his life. Some new innovations. We are doing also spinal cages. This is where we need to play. In this area, if we talk about niche applications, osseointegration, you can print this very fine lattice structure with the screw thread. And I am really happy to say that we manufactured now from the beginning of this year to up to now 1,500 spinal cages. That was customized, you know, some of them are patient specific, some of them are different sizes. And to end up here, you know, it's not just, and you can ask the guys that do have some of these machines, it's not just buying the machine, press the play button and the parts fall out. There's really a lot of research and innovation that need to go into this. I'm just happy I didn't wake up with x-rays like this. You know, it must be quite painful, but at least the clinical evidence, all of that is looking very, very good. Just also some new applications. So maybe it will be great if you can print a PMMA cranial plate that's strong enough. We tried titanium. Titanium is not perfect for cranial plates. You don't want that, because if you need a second CT scan, you will have scatter. And we went on a study visit to Brazil, and they print a male and female, and they buy the bone cement, take it into theatre, and you manufacture it there in theatre. So we've done that now. Similar, that we can, inside theatre, you could see some of these cases where we can form, if I could say it like that, you know, these PMMA. Patients on the waiting list, so sorry for this, but these are some of the kids that we are helping now. That's the lady that was operated on the other day. But this is the biggest. We are busy with this. It's in the state patient that will be operated on next month in Kimberley. So just lastly, just on the qualification, why is that important? Because again, if we want to have 5,000 spinal implants, we had to already started in around 2013 with the qualification of this process. I actually touched on this collaborative program that's funded by DSI. Yeah, and I even do have the new logo of DSI. So that must count for something at least. I know. You will see the different partners throughout the country. I'm not going to go into a lot of detail, but what is important for us is to generate validated data. That you can have at least from the powder, from the process, the post-processing, all of that. There are many steps, and non-destructive testing, destructive testing. If I show you, I'm going to skip a few slides. This is how complex the process is looking like. And this is from Siemens. And if you have a look at all the different influences, like on the pre-processing, the process, post-process, then you need a quality management system. We actually went through that process. I know there are two other companies, one from one company, MAXILLARY, that I heard that received also ISO certification. So this is to design and then to manufacture these devices, the implants, the pre-operative planning models. Just to show you quickly, this is how the process is looking like, that we go through from where we design, get the prosthesis request, the monitoring. I will play you now a last video about this process monitoring and how the machine manufacturers actually look at this and how they can generate in-process monitoring, while the process is running. So this is the video, and then I will end off.
EOS State Monitoring Suite provides deep insights into your parts in real time. This allows you to detect flaws in parts and stop the building process when a failure is detected. Especially in the aerospace industry, meeting high-quality standards is a major requirement for serial production. To ensure profound quality assurance for metal 3D printing, the EOS State Monitoring Suite comprises 4 powerful tools. Developed with MTU aero engines, EOS State Exposure OT captures the entire building platform with optical tomography and provides a holistic view on the melting behavior of the material. This tool is optimized for quality assurance and helps to lower the costs for CT scans after the build process. EOS State Melt Pool measures and analyzes the melt pool behavior in real time. This enables you to detect part defects and analyze the homogeneity of parts. Also, EOS State Melt Pool provides deep insights for your process development. EOS State Powder Bed monitors each recoating cycle to detect recoating failures or particles in the powder bed. Finally, EOS State System, in combination with EOS State Laser, monitors the basic process influencing conditions such as axis, atmosphere and temperatures, laser power and online laser power control. Understand your process better. In every part, in every layer, in every spot. With EOS State.
Yeah, sorry, I'm not promoting EOS. We do have a lot of EOS machines, but I think what's very important is that they think of this already. That we don't need to non-destructively, scan all, micro-CT scan all parts. That we can validate through this, we can validate the different parts. Also, quite exciting news is we will launch this project, medical device additive manufacturing technology demonstrator, hopefully in November. That's funded by DSI, and if you have a look at the spinal cages, like that company can't afford to go through a full ISO, a full ISO process to acquire the machines, to develop, to put all the R&D into product development up to a stage where they can have 1,500 parts. We want to partner with industry, to bring their ideas and then to do the R&D and then to manufacture up to a point where they are comfortable that they can buy their own machine. We can help them with the process validation. But I think this is a very good initiative, to be honest, to support medical device manufacturers in our country. A big focus on additive manufacturing and then the medical, but it's not just titanium. We want to bring in, you were talking about new materials, but cobalt chrome for dental applications. That will be our next, one of our next view. And then just to show, we are playing from TRL and CRI levels really low. We have pure research, applied research still, but application driven, and then different centers inside the university that plays different roles. Very interesting is the DSI funded, Merceta funded chair in innovation and commercialization that really wants to see the impact in industry. And then I just need to thank all the people. It's not me, it's really, you can see passionate people. That's actually a small team that's doing the work, and then all the acknowledgements. Sorry, I will need to get 2 slides, but thank you very much to the NSTF also.